All right, we're back. And today we do some housekeeping. We need to do housekeeping because since the last iteration of the part tumbler, we went on a side quest and we did some design on this open source framing. And so I want to clean up some assumptions and double check some work on the open source framing project here, um, which is this. So catching anyone up who's seeing this for the first time, this is 8020 extrusion slash mod truss slash really any modular framing system replacement. It uses a snap fit system like you see here. We did some calculations on this. We did some design. So I want to clean up some of the work we did around calculating the sizing charts. I spoke to a friend who got a degree in mathematics and asked them specifically about this equation here. Yesterday, we talked about solving for L here, and their recommendation was we could use the Newton method, Newton's method, um, but recommended actually that we should go back to our initial derivation and see if we can split these terms out and find a way to do this calculation without having to do the crazy stuff we saw yesterday in Wolfram alpha. So that's one. The second thing I want to do is go back to the part tumbler design and talk about how we calculated the maximum or the ideal radius for finding the optimal speed of the motor to spin that assembly. I might have made a mistake, so I want to go back and clean that up. And then we'll get into design for the part tumbler here and talk about, well, actually go back and just implement some notes, specifically around the build of the new hatch and the the barrel sort of fabrication method we're using for that. So finally then, if we have time, we'll go into designing the um, next version of the prototype. So this is revision, or this is type A. I've actually got the parts made for the CNC slash casted version, which is type B, I believe. Or I have it for type C and type B. And they're essentially the three types of the part tumbler that we're going to go through and implement some notes on. So those are the four things I'd like to try and get to today. But we will start on that framing and rederive some of these equations. So what we were trying to do here was find a way to relate for flexure, specifically this flexure, what the optimal geometry was for that flexure. So I'm actually going to draw what these values were. So we had length of the flexure, which is essentially this distance. This is L. We had the width of the flexure. That was B. And the height of the flexure. which is h. So actually, I think a better way to draw this will be to draw a cross section like we did prior. So we'll do AA. And that cross section AA looks like, see if I can crop this. Still haven't figured out how to crop. That section AA looked like this. So we had H, which is also equal to T. We'll get to that in a second. And then we had B, which is also equal to width. And so we'll write that out here. So H is equal to T, which is equal to thickness. B is equal to width. L is equal to length. Actually, so we can just type this out. Okay. So let me see if I can get this in a way that makes sense. I had some good feedback today from a friend of mine who pointed out that it's really hard to jump into these streams and understand what the hell's going on. So that's what I'm going to try and do today, is see if there's a way to make this a little bit easier to understand as we go through this stuff. Got my calculations over here. So let's rederive this equation here. So we want to rederive this to get it potentially into a place where we find a better layout of the terms so that we can solve for L more effectively without some super long equation. And to show what I'm talking about here, I'm actually going to pull up ChatGPT and write it in LaTeX. And we'll feed this in Wolfram Alpha. So what we want to do is we want to solve for L. L was the goal yesterday, right? And that's a function of all these variables. What we found was it was really hard to do that. So we're going to write this out in LaTeX. And then we're going to double check it. And we're going to feed that into Wolfram Alpha, which is Wolfram Alpha is essentially a math engine that will just solve crazy stuff for you. So we'll input this and we will see if it looks right. So delta's right, E, B, H, Q, blah, blah, blah. That's all looking correct. Great. So we're going to go to Wolfram Alpha. And we're going to ask it nicely to, actually, we're going to go back to ChatGPT. We're going to ask it to solve this equation. And so ideally, this spits out some solution. And this was the solution from yesterday, and this was the problem. Essentially, you can't really, I mean, this is crazy. This is insane. When you see something like this, something is wrong. So you got to go back and figure out what you did incorrectly. And so we're going to rederive to avoid this. Technically, we could go solve for this, but um, there must be something we did incorrectly. And so what the goal is here, by the way, is to get a function that for these inputs in this equation gives you an answer. And what that answer is supposed to do is, I'll take you to the GitHub. That answer is going to replace the chart that we have here. What this chart does is it shows you for a given thickness of a material. So in other words, how thick this tube is, or how thick this flexure is. What's the length required here? What's this length? What's that gotta be? So that's what we're looking for. And so this chart was the answer for that. But it would be awfully nice, instead of having all of this code, if we could instead replace all of this code with one equation. And that's the goal. So if we do this correctly, we can rederive this and potentially get to that. So let's do that. Remember, this is what we got when we tried to do that, when we tried to solve this equation. We get this, so something's wrong. So let's go and try and rederive this equation. So the equations I used to solve this were the equations and shear and moment diagrams for a cantilever beam, which is essentially what our flexure is. And so the key equations here were deflection. So here's deflection. So we'll call this equation 1. I'm actually going to copy this over here. So that was one equation. The other equation was bending stress. That's the other equation. This is equation 2. And finally, the third equation was the von Mises stress, which was a combination of torsion, and bending. So we won't go into the derivation for this because I don't think it's relevant, but these were the 3 equations. When you substitute them all and manipulate them correctly, you end up with this. So this somehow gets spat out when you combine these. Get this. So we're going to find a better way to do this potentially. And if we can't, we give up. I'm not a proud person. So let's do that. So we're going to rederive. So we're going to first go through and talk about, we'll start with 1. We have to put this in terms of B and H here. So we're going to do that. So I is second moment of area, and I is equal to BH cubed over 12. You'll have to trust me on that. I'm not going to rederive everything today. We're just going to just keep moving. That second moment of area, and that describes the resistance to bending in a beam. So we're going to put that into 1. See what we get. So deflection is equal to PL cubed over 3 E B. And remember, we're substituting this equation in for I here. BH cubed over 12. And so then we start to simplify, and we get del is equal to 12 P L cubed over 3 E B H cubed. 3 EBH cubed, yep. And then this simplifies to 4, because 12 over 3 is 4. So now we have this equation in terms of, call it 1A. This equation in terms of the dimensions of the flexure. So we actually start to relate thickness here. We're going to do the same again, but for bending stress. And so for this one, we get, again, we're substituting I in to this. We get bending stress is equal to MC over BH cubed over 12. And C is equal to H over 2. That's because C is the distance from the center of the beam to the outermost fiber. So now with that, we implement this new value into C, and then we solve and simplify. And we get the bending stress is equal to 12, because this term down here just comes up to the numerator. MC over BH cubed. I'm sorry, this is in C. This is H over 2. BH cubed. So we have 12 over 2, which is simplifies to 6. Not B. Don't get them confused. Okay. So now this is 2A. And so now we still want to relate Actually, did we need to do this? Yes, we still need to do this because we want to find our h's. And actually, the h there cancels out, so this becomes h squared. And m actually is the moment, which is actually moment is equal to um, the load times length. And so there we go. There's how our L plays into this now. And now I'm starting to see why this was not solvable. Okay. Then we finally end up with wanting to solve for this equation, 1a. And I think we try to plug in p. Yeah, so we want L. We know all this. So we want L. We now have stress that is described by this beam equation. So we're going to plug 1a, sorry, we're going to plug 2a into 1a. And we get del is equal to, well, actually, first we have to solve for p, and we can plug it into this equation here, because again, we want L. So 2a turns into sigma b times bh cubed right? I'm sorry, bh squared, because this comes up to the numerator over here. And then this becomes, we move the L, no, yeah, we move the L and 6 down here, 6L. And that gives us P, and now we can substitute this into this. So now we do 2a into 1a, and we get del is equal to 4p, but p now becomes this, sigma b, b h squared over 6L and so that's our P here. Now we move on. L cubed over E B H squared. Now it's just algebra, so we'll just keep solving. So we'll bring the terms down. So 6L times E B H squared. That should be it all. That should be all. And so then this turns into 4 over 6, the common, it's 2/3, right? Yeah. Yeah, 2/3. So 2 over 3. And then we get sigma b. And then b cancels out. H squared cancels out. Actually, we want that to be legible, so I'll just use a red line. So these cancel out. And then we get this as a function of L cubed. Right, so 2/3, that goes away. Sigma b, bh squared goes away, L cubed, then I have L e. Okay, so let's just double check this. 4/6 turns into 2/3. Sigma b there, L there. Bh squared goes away. E, L cubed lives here. So I think this works. That is our solution. And that actually might be solvable. But it doesn't factor in our thickness and width. Interesting. So what we're seeing now is that our geometry actually doesn't matter for the length. Really, the sigma b is actually a yield, but I'll signify that here. Sigma b, we're saying roughly is equal to this factor safety and our yield stress, which is really just the stress. So we'll get rid of that subscript for b. Okay. So what we're seeing here, well, actually, let's solve this, and then we'll talk about what this is telling us. So this L factors into this L, so this turns into L squared. So we get 3e. So now we solve this for L. So this becomes del, pull in our 3e, right, because that's going over here. The denominator is going over there, is divided by 2, because the numerator is now coming down here. 2 times the yield stress, and that's equal to L squared. And now we square root this. That's our answer. So now we have an equation that tells us how long our flexion needs to be given of all the parameters. And so there's a couple interesting things going on here. Let me pull out the original equation prior to our solving it. Actually, I'll make this easier to understand by color coding it. We're trying to. Can I stroke all this different color? Yeah, there we go. So this is what happened. We fed this equation. We fed it length. Okay, taking a step back. We're solving for L. We want L, right? We gave it all the parameters we had for this system. That was yield stress. That was the geometry of this flexure. It was the geometry of this flexure. This keeps going away, so maybe I'll just grab a screenshot of this. Sorry, but you're all learning how to stream with me in real time. Okay, so what this is showing us is here are all the parameters on the left. We had the geometry of the flexure, which was the width, was the thickness of the material, which was h. We had L, we had the modulus of elasticity, we had all of that. And we derived that earlier by combining the stress in the beam and the deflection of the beam. And interestingly, what we found was that when you simplify this equation, most of the terms cancel out. And what you find is the required length of a flexure doesn't actually look at load. It doesn't actually look at the geometry of that flexure. That's actually um, crazy to think about, but it doesn't matter. All that matters, this equation is saying, is how strong is your material? In other words, what is the yield stress? What is the stiffness of that material? What is the modulus of elasticity? And how much does the flexure actually need to deflect? Those are really the only three things you care about. And if you know those three things, you can spit out what the required length of the flexure is here. That's interesting. So there was a solution, and we just derived it incorrectly. And so in theory, we should be able to go back and spit out these charts just based on this equation. Very cool. Okay. That was worth doing. This is why, by the way, I think this is why you should always be trying to derive from first principles your 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 design, because if you had just gone to straight to FEA and started designing, you would have endlessly iterated and looped without understanding the underlying engineering and scientific principles behind why you were changing your design. It's kind of a meme, and I see people joke about it, but people joke and mean that, well, just run FEA and forget about it. Well, yeah, but you'll be running FEA for days or weeks or months because you want to understand the system. So as you're trying to optimize, you don't know what you're optimizing for. What this does, by solving from first principles what the actual behavior of the system is driven by, when you work from first principles and understand the underlying mechanics, you shorten the time incredibly by knowing what you're optimizing for. And so here, we know what we're optimizing for. Do we want a super long flexure? Then we want more deflection and we want a stiffer material. Do we want a smaller flexure? Well, then increase your stress a ton, or make your stiffness lower and your deflection lower. So that right there is invaluable. And even more invaluable is the ability to do it. It takes a lot of doing this to understand how to do that. Anyways, okay, so housekeeping part one done. The second one was I wanted to second guess or double check my work on understanding what the acceptable or the maximum speed for the tumbler was. We'll look at the CNC version for this one. Actually, this one we don't really have working yet, so let's go look at this version. Okay, so what we're doing here is we're trying to understand what is the maximum speed you can spin this barrel. Let me clean this cat up first. What we're saying is, for a part tumbler, what is the maximum speed you can spin this thing before the media in the center starts to stick to it, it being the outer diameter, and stop tumbling. Ben Krasnow at Applied Science just did a video, I think his penultimate video about this, and talked about how essentially you need a rotary ball mill to overcome the fact that gravity limits you here. So we want to find that maximum speed. And I think I did it incorrectly potentially. So I want to go back and just double check that. To talk about what we're talking explicitly about, what is a part tumbler? This is a part tumbler. Let's find one that we're competing with. This is the one that I've been gunning for. I think I got the bill of materials down to this cost, essentially. But we're actually better because we have way more area. I'm sorry, volume. We have way more tumbling volume. That is hilarious. Look at that. That is a solution for sure. Yes, this is what a part tumbler does. Let's see if we can find a video. Essentially, it takes parts and it finishes them. Makes them look really nice. So all this does is it literally just spins. But when you put in media, and so your media is just rocks, but it's essentially your tumbling material. When you put that in, it smoothens out your part, removes the rough edges, cleans it up, makes it look really, really nice. I don't know if I have a part in front of me that looks like that. Um, yeah, I don't have a part right now that is tumbled, but the goal is to be able to do it on 3D prints and stuff. So here's a prototype actually that just came off the printer. So if you put this in a tumbler, I don't know if you can see it, but these edges and layer lines are pretty rough in some cases. And that's what the tumbler does, is the tumbler gets rid of those. So that's why we're interested in a tumbler. And if you want to create products, you definitely want a tumbler. If you're going to create products, you actually want more than a tumbler. Like when you buy a product like your car, for example, even the components that aren't consumer facing or customer facing go through a incredibly rigorous kind of finishing process. The ones especially that are customer facing they go through an incredibly rigorous finishing process. Part tumbling is one of those steps in many cases. You'll also see things like bead blasting, and even manual sort of surface finishing where to actually burnish a surface, they'll actually just take a burnishing wheel and actually manually clean up the surface. So that's why we care about the part tumbler anyways. So I wanted to work through the physics on that real quick, because what I realized was we actually didn't work out what speed the speed was. So really, you want to make the speed as fast as possible. You want to make the speed as fast as possible because see if I have those calcs. Don't. It's all right. I'll just start over. You want to make the speed as fast as possible because it's energy in equals energy out. And the more energy you put in, the faster the finishing process takes place. So here's where we did last time, and I want to double check this. So the way we're going to think about this is, don't worry, we'll get to CAD soon. I did not want to do more calculations today, but we'll get to CAD soon, right after this. So you have your wheel, which is this, and let me see if I can just draw on the thing. So you got your wheel, and it has a center there, and it spins at some angular speed, omega. It has a distance from the center to the outside of r, and we want to know what is omega max. Or in other words, exactly, Jake. We're trying to find so the minimum speed is 0. In other words, it's not spinning. 0 energy going into the system. We're trying to find omega max. What is the maximum speed? And that is the maximum the parts are still being tumbled, i.e. not sticking to the outer walls. That's what we're looking for. So what that is, let me talk about, well, I'll just draw the free body diagram on this. Can I do it? Yeah. So what that means is you have your barrel, your center. There's going to be a center of mass on the part right there. And that is going to be some distance r. And we have here, actually, let's just draw the free body diagram instead. You're going to have force and tension. You're going to have mass of gravity. Yeah. Forces of tension, mass of gravity. And then you're going to also have your you're also going to have your MA essentially. So those three are going to be acting here. And when you sum them, you essentially get force of tension plus, and I think, no, MA is actually going the other way. Plus mg is equal to MA. So what is the force in, it's the, what's MA and F equals MA for a rotation. I think it's mv squared over r. That's not right. It's not it either. Just had this in my, seen this in my physics book. We'll derive it, but we got to get angular acceleration. Why is this not giving me a good answer? So let's see if I can pull up my physics book real quick. Can't. Okay. Keep sleuthing on the internet then. Getting closer. There we go. V squared over R. That's what we wanted. So A is V squared over R. So then this becomes force in tension is equal to, it's plus actually, not equal to, mg, which is equal to m v squared over r. I'll make this lowercase r so it's not confusing. And then we set, so we're going to say, okay, when this is spinning it as fast as it can, it's going to just, when it's spinning as fast as it can, F the force and tension essentially of a theoretical cable tying the mass to the parts would start to increase the faster you spin. And so that's what we don't want. We don't want the parts sticking to the outside. So the maximum would be when this just starts to go slack and you get 0 as the force of tension. So you set F sub t equal to 0. Then we get mg is equal to mv squared over r. M cancels out. G is equal to v squared over r. And then finally, gr is equal to v. The square root of that is equal to v. But this is actual velocity. And so we want to put this in terms of angular velocity. And angular velocity is equal to, yeah, we want this in terms of angular velocity. So let's just write this over here real quick. What is angular velocity? I think it's v over r. It's v over r. v over r. And so we're going to replace v with that. So v is equal to angular velocity times r. So then we substitute that in. Gr is equal to angular velocity times r. And then finally, we simplify. So this becomes gr to the 1/2 power, because the square root of something is the same as the exponent of it to the 1/2 power. We bring r down here. That's equal to the angular velocity. And then finally, let's move all this back up. So we solve here, and I think this is, I haven't done this in a while. I don't know if I'm going to do this correctly. So gr 1/2. So this is actually the same as gr 1/2 times r to the -2. Isn't that right? I haven't done algebra. I haven't done exponents in algebra in a while. What is it? It's it's negative. Oh, -1. That's right, -1. Right. And so then, yeah. And so then this becomes gr to the -1/2 is equal to omega. I think that's right. Or is it, it might be this. Square root of g times r to the -1/2. And that's the same as g. I'm gonna have to double check this in a second. It's equal to square root of g over r, I think. Which is what we had before, I hope. I think it was. What was it? Yeah, g over r. Let's check. What did this? No. Wait, what? That's wrong. Wait, it's not seeing it correctly. Whatever. We'll write it out. What was it? It was gr is equal to wr. I think that's not right. All right, we're gonna have to. I mean, come on, it's 2025. Why have computers not figured this out yet? Okay, what are we gonna ask? Rules for managing exponents. Actually, what if we fed that into ChatGPT? Let's try this in ChatGPT. Yeah, okay. I was right about my exponents. All right, so we did this correctly the first time. And what this tells us is we're limited by gravity and we want to make the radius as small as possible. Okay, so we were right. So this needs to be small. Now, the downside is that when your radius is super small, then you get less volume. Volume of a volume of a cylinder is equal to pi r squared. That's your area, right? Here. Um, Actually, it's pi r squared over 2, but that's your area. And you multiply that by the length. And so the length is just the length of the barrel. And here we're saying we actually want the r to be really small, which means we optimize for maximum tumblage, but we hurt ourselves in terms of optimal volume. So it's a difficult decision. But the way you counteract that is if you want the same volume, but want to tumble it faster, then you just make it longer, which is actually interesting. It's probably why when you look at bar tumblers, they tend to be long and they tend to have long barrels instead of just being giant discs like this. These are vibratory tumblers. That's why they don't care. They don't actually spin. Okay. All right. So that's housekeeping items. Let's get back to actual design. So this detail, there was a couple things that I learned from this. The first one was the material is way too thin. I used 1.6 millimeter thick uh, aluminum, and you can see uh, it ain't strong. That's point one. So here's the actual part I was pointing at. I had two made. You can see I can actually bend this. Like, it's not doing anything I need it to. What we want is something like this. It's for a random prototype I made for something. And this is 3/8 inch thick, and there's no way, no matter how hard I try, I'm going to bend that. Yeah, no way I'm going to bend that. But 3/8 is too much. and it's also expensive. So we're not going to do 3/8. I would rather do maybe quarter. I think quarter is going to be okay. If I have a 1/4 inch plate lying around. No, I don't. Quarter it is. So these go to quarter. The second thing I learned was these don't actually do anything at all, interestingly. So, I mean, you can see there's a gap there, so they don't really do anything. So just to prove the point of how weak these are, I'm going to bend these out of the way and show you. So I just bent this out of the way, and you can still see that the shape is retained. So same with this, bend that out of the way, shape is still retained. So all I really need to do is find a way to get this hardware to pre-tension the brace on the bottom, and then I get my shape, which is good. So that's what we're gonna do. So that's the two things. Actually, I'm gonna write this down. Come up with a to-do somewhere. I think we already had one. Here we go. So make braces thicker. We also don't need the detail on the top, so remove portion on the top. Well, we can actually, because we do want, we actually still need this, because that's where we have our retainer, our locking feature, I should say. We don't have room to reverse it, I think. Remove portion on the top that we can. What was the other one? Remove visible portion. What else we say? Oh, brace. I don't think we need the brace. The brace is this. I don't think that's doing anything either. Oh, and then we want to add a slot detail to one side of the hardware. Probably this one, but essentially lining these two holes up over that bend has been really difficult because I don't think that the flattening is working as accurately as I would like. So to release the dependency on that tolerance analysis radially along the length of this hatch from this hole to this hole, we're going to just turn this into a slot. Okay. All right, so we can get to work on that, I think. Okay. What we're going to do. Let's start with thickness first. Let's get this in scope of the entire assembly. So I think we can do 3, 6.35. That's kind of thick. I think 1/8 inch will be stiff enough. So we'll do 1/8. Actually, do we actually need the additional thickness? Because we're not going to do this cantilever anymore. No, I guess we do because we still have this tab we care about for locating this thing. Although, huh. Actually, I think there's a way to build this out through a hole in here to pick this up, and we don't need the overhang, and we don't need. Yeah, I think we can make that work. Let's model that first so you can see what I'm talking about. And actually, that's great too because I think that means no, it doesn't mean we can make this the same. So we'll leave this in its current place. Actually, I'm going to do some moving of some items here to make it easier to look at. So we will actually get rid of some of this geometry. Let me pull a section up real quick, get a better view of this. Okay. So we're going to flip this hardware. We're going to have to redraw this from scratch because we don't want this brace anymore either. So I think we're just going to have to redraw this from scratch. That's okay. Direct modeling to the rescue. Okay, not working. It's fine. So we will copy this. We're just going to pull this area here. Actually, let's pull this line all the way out. And then pull this one too. Okay. So we want this. We don't want this. We do want this. That's the key geometry right now. We want to be 3.18 this time. New body. There we go. Then we're going to delete this. Actually, we're not going to delete it yet. We might actually need it. So just get it out of the way for now. Actually, I forgot to clean this up. There we go. Okay. So we want that. We're going to want to reverse this. We'll just delete that for now. And this we're going to, I think we can actually just delete this one. Why is that deleting this body? Who knows? Okay. Wait, why is that? Oh, these, I see. Okay, so we are going to select the barrel. So now let's see if we can mirror this and rotate this into place. So where's my hardware here? I want this hardware as well. Actually, this washer didn't work, so I'm gonna get rid of that. I tried at install to do it, but there just wasn't really room, and it wasn't really doing anything anyway, so. Okay, we have to rotate this into place. I think I did some nominal, like a degree or something like that. Might have been 5. What I'm trying to do is just rotate this hardware detail into the right place. 3, 4. Looks like it was 4. Yep. All right. And so then we're gonna then draw this to join here. And then I think that's actually pretty quickly done. We don't need this slot anymore. We don't need this one either. That was fast. Am I forgetting anything? I think we might need this to come out of here to help define this curve, but I don't think it's really going to do that. So we actually need to modify this barrel because it's going to be tangential here. So yeah, we're going to have to modify this. What I'm saying is I modeled it here correctly. Essentially, this screw is going to preload the wrap around the skeleton, but it will only do that to a certain extent. Essentially, where it no longer is supported by the by the skeleton, so we have to change that here. It's going to follow, it's going to stop following the curve and start deforming to the natural shape, which is flat. I have to draw that manually. Look right. Does. Okay. We'll compare this to this. Huh, I'm realizing fault in the design. This is overlapping. So this was going to collide. I'll show you what I'm talking about. So when you rotate this part about this pivot, it wouldn't actually open because it's going to collide with, there you go, this part. And the reason for that is this is overextended over here and it shouldn't be. So we need to fix that. Good thing we checked. That was a stupid mistake from the first release. Should have caught that. So bring this in 3. Yep. And then we will do our check. I think we want 60 degrees. Looks a little too long there. So pull that back. 1, try again. So we'll rotate this again. Just kissing here. And it looks like we do intersect with that. So let's go back to this movement here, this face offset, and tool that up to -3. It looks like we don't interfere with that now. Gets close here, but we don't. Actually, we should be careful with that though, so let's make that 5. And it looks like it does not interfere. looks good. Gap's a little big though. Not sure how I feel about that. We also have to pick this up, so we were definitely not done. This, I'm gonna restart CAD real quick. The clicking is annoying me. Okay, we can actually pull that geometry from here. Yeah. Just joining these two parts real quick, but it isn't cooperating. There we go. My radius here, 5. Okay. Ooh, we actually, is that gonna work? Let's do the rotation check on this now. This hatch has to open and close, and so it has to not interfere with the barrel here. Looks like it doesn't, weirdly. Yeah, that sort of defies my intuition on that, but we should increase this radius to reduce the likelihood of that interference. Okay, looks good. Actually, these don't have to be, well, no, I'll leave that. No reason to change that right now. Okay, so now we can start to pull this curve in a bit. That was kind of the point here. Well, no, wait, I think we're actually fine here. We don't need to really change this. We're fine there. All right, so we want to add this tab. To this. And this is going to keep the locking mechanism attached. That's why we care about that. So what we'll do is we'll actually just sort of slice this around to make room for this to come up through the through the wrap. We can add some cutting relief. Do that now. Should be able to mirror this. Pop that plane, that line. Make subtract these. And our cutting reliefs there now. Okay. So the problem is now we have a cutout here that allows for media to get out while we're tumbling. So we have to fix that. Wonder if we can just insert this from the bottom. Add a little clearance. Give it 0.5 millimeter. So we'll give it a 0.5 millimeter all around. So we're gonna give it more than that, because we're gonna have to add a cutting radius here. Cut a relief. And that is going to eat up our gap. So we'll give it another millimeter. That is a thin wall condition, so we might not be able to do that. What is our distance? It needs to be at least... Oh no, we're fine. We have this material there. That's fine. 8.6 is plenty. Okay. Does this actually come off? Because this seems to grow a bit. So why don't we rotate this, because we don't need the material on this side. So we will find that step somewhere. Yeah. We'll get some clearance here. Is 10 enough? 10 is probably fine. Do 10 here too. That looks goofy, but it'll look better in a second. There we are. Okay, cutting reliefs slot for the plunger. We'll move the plunger back so you can see what this is doing. I have this off center because I want to generate preload in here. So when you actually move this up just a hair, it'll actually preload the entire hatch into, well, the barrel. That's why we're doing it that way. And I think we might be able to delete that here in a second, but we'll wait. See if we can get rid of this hardware because we're going to mirror that over. And then we will actually get to mirroring. But let's pull this section, double check. You know what? This I find aesthetically displeasing. So we're going to fix it. We draw the circle that, well, that's part of it. Okay, we're going to draw a circle that is tangent with this curve. Doesn't make sense. We'll do this instead. Make a tangent to this. Okay. And now extrude that out. Delete this. Delete this. Looks better. Okay. And then finally, we're getting there. I think we can just, this gap is killing me. I mean, this is going to be, it's going to be a problem, right? What's this distance? 8 millimeters. 3/8 of an inch. Might be fine. I mean, we'll try it out. Doesn't work. We'll learn. Let's put our radii here. See if we can start. Making this make sense. So now I think we'll mirror this over now. We'll have to create a midplane to do that. And create a midplane between the two faces that we want to mirror our hardware and parts through. And then we mirror. And we retained this hardware, this feature for keeping the spring plunger for locking the hatch. So we'll just delete that. We don't need it for this part. And I don't particularly care about symmetry or maintaining part count. So now we can delete this, and we should be able to, keep it that way. All right, let's do a sanity check. Let's pull our cross section through. Oh, I forgot. We want to make this a slot as well. So we'll do that now. I'm gonna get a plane right here in the middle of this hole. It's gonna be a radial slot, that's why I'm doing it this way. Okay, then we'll rotate and copy this. Why is it not working? What's going on? Why is 2 degrees unacceptable? Just have to constrain this. So give that 1 degree. Probably okay. I mean, call it 2 for giggles. Yeah, 2's fine. Well, actually, I don't have any justification for that. And my gut is telling me that might be too much, so we'll do 1.5. Okay, so now we should be able to extrude this. And what was the original diameter? 4.5, so we want that to be 4.5. Come down into the history to pick that up. So 2.25 to make it 4.5. And then we will, why is that goofing up? What? Double what? What's going on here? Oh, what is going on there? Let's delete that. I think that worked. I mean, it's good enough. We'll delete this. Yes. And then we'll fill out these edges. And then we will mirror this to the other side. Double check that hardware lines up, and it does. And yes, it does. We are good. We can slap a washer on that if we really need to. Okay. Let's look at our to-do list. So we made the braces thicker. We removed the visible portion. Yep, did that. Got rid of the brace and added a slot detail. All right. Wow, that looks so much simpler than this idiocy. I guess what we didn't know though that we were gonna have the stiffness, so that's why we had to do it the stupid way to start. In our defense, we had to do it the stupid way to start. Then we learned, and then we undid the stupidity. That's why you build and iterate quickly. Because all that fancy analysis, it's just fancy analysis. And it needs to be validated by building. If you aren't shipping quickly, you aren't shipping. Is that a quote? It's not. All right, I'm going to patent that quote. All right, so that's, I think, this version of the tumbler done. We're gonna wait for parts. It's that one right there. And so we're calling that P Tumbler Mini Tough. So you're in marketing and can help me come up with a better name. Please, please. In the meantime, it's called P Tumbler Mini Tough dash A dash O now 3. Actually, I should make sure I get that set up correctly. I don't want to lose that revision, so. So I can pull this back in history. And I can't. Kind of. Well, lucky for me, they just implemented the versions feature. So I can go look at the versions and get an older version of it. And I'm going to want the 19th. How cool is that? First time I've used that. It's pretty useful. Move that into revisions. Okay. So that one's done, and now we're working on this version again. We might copy that hatch over. So I think we said we were going to do mostly PEM nuts. We can make this smaller. So we'll do that once we validate the design. So yeah, let's just go over the list and then we'll start going through the list. So we're going to change nuts to PEM nuts because they're more expensive, but they are way better at install, and install matters to me right now. We're going to extend the flaps at the top of the barrel for overlap to address tolerance gap. Which one was that? Extend flaps at the top of the barrel to address tolerance gap. Hmm. Oh, this one. This one right there. Let's do that. I think we already did that one too, actually. Just to be safe, though, we'll add a little bit more. Okay. Increase screw clearance on attachment flanges. Yeah, I think that was this one. Hmm. Can we salvage this part? I don't think we need to replace. I think we need to replace these, thankfully. All right, keep going. Slot details. Yep, that makes sense. Bend slot. Yep, that makes sense. Actually, I was thinking about this. I think I can just remodel these in a way that makes these easier to actually unfold. So this problem will go away, potentially. Not go away, but we'll be sure that we get them all as a check. We'll leave this as a reminder. Redesign of the latching flexure. Yeah, that was also partly because we didn't actually get the barrel really working yet, so. And as a matter of fact, I think part of the reason why the barrel wasn't really working was the diameter is too small. So that's becoming a constraint. So the larger that diameter, we get more volume, which is nice. But actually, with that said, why don't we pull up this calc and see what the theoretical diameter maximum is? So we actually do kind of care about that. We did the math here. And we said it was 100 RPM. Okay, well that's good because that's saying that's great. So that's saying our 20 RPM current is plenty. I'm sorry, it's nowhere near the theoretical maximum. We'd have to spin 5 times faster to get to this actual theoretical maximum. Our current speed is 1920 RPM. And actually, that reminds me, that motor, I got it built into the CNC prototype, and it was absolute garbage, so we're going to have to change the motor. That's good because, like I said here, we might be changing all that. All right, so this is going to be, I'm going to go on mute for a second while I type this all out. All right, what I'm doing is I'm getting units in here, and G for gravity is meters per second squared, and then radius is just a meter. Per second RPM, that's not right. It's unitless per second. Does pint have manipulation revolutions? Angular frequency. So they give us hertz. This is nuts. They gotta figure this out. Let's print a mega to see what that is first. Yeah. So that's radians per second. Just to double check us. Yeah, so that's working. So our theoretical maximum is 10 RPM. I mean, 100 RPM. This, let's actually make this in millimeters, so I just feel better about it. I think we're at 100. That all stays the same. That makes sense. And we actually, the center mass is actually going to be a third away from that. So we'll call it 66, and it just goes faster. As we talked about earlier, R goes down, speed goes up. We need the, I wonder actually, this is actually a good exercise. What is our, here's something valuable to know. What is our maximum barrel diameter or a given RPM dictated by motor sourcing? So we had this equation, And we're going to rewrite this in terms of r. So we get omega squared is equal to g over r. We flip omega and r, and we solve again. So just do that real quick. So we get r is equal to g over, is that right? Yeah. So we square that, we get omega squared, that goes under g. So we flip, so we undo the square root, we get omega squared. We flip omega and r, and we get r is equal to g over omega squared. Yeah, so let's write that out. I have the motor speed dictated here. Motor speed we do. 10 RPM. Actually change this to 19 though. Actually, let's just make this something we can tweak down here. What value do we want out of that? Just radius, I think so. Unterminated F string. Ooh, that's a big barrel. So what happens if we make it 20? Okay, we're getting close actually. Well, not close, but so I think we're still 10 off away. We can make this barrel much bigger, and we don't have to worry about getting to the critical speed. So we can make this barrel bigger. We actually want to make the barrel bigger though, because it assists with manufacturing, but I don't know that we really get anything for it. The software Shaper 3D runs on Mac, Windows, and iPad. Runs really well on Mac, as you can see. Okay. Guess we can increase the diameter of the barrel. I mean, we really should just resize this entire thing. All right. The resizing the barrel is going to make it so that we can form this thing less painfully. And we won't get the sort of deflection you're seeing in the back here, or the deformation that you're seeing in the back there. Yeah. That's what we're gonna do. We're gonna resize this entire thing. And it's gonna be a lot of work. But not a lot of work, just it's gonna be some work. Maybe we're gonna have to change these two though. That's fine. We also want to change this hardware. I think we mentioned that. So why don't we do that real quick? I'm gonna pull that from the other design. It's not right. There we go. Clean this up too. Okay. And then I think we have to move this. We will eventually. Actually, I think I can move it now. It should work. We'll double check that later. Okay. And just for sanity, let's mirror this about that midplane. Yeah, that works. Great. We'll rename this. All right, so we're going to redraw this now because we're going to get to a larger diameter. And I think we're going to do that. We'll get started on that tomorrow. Yeah, we'll get started on that tomorrow. All right. So that's it for today. And I'll see you next time.